I began working on a popcorn roaster modification for my specific purposes about 6 months ago, and I've been posting my progress and problems that I've encountered, solutions to those problems, on homeroasters.org, on a specific forum that they have for popcorn poppers. I've reached a point finally where I don't really think I can do much more than I've already done. So one of the ops there on the forum suggested, why don't you do a video at this point to show the other people on the forum what you've come up with and where you've ended up. So, just to sort of give you a little bit of background, before I got interested in roasting, I was interested in brewing. And I tried a lot of different brewing methods and wound up with the AeroPress is my favorite. The reason for that is that, it allowed me to brew 1 cup or 2 cups at a time and also control all of the important parameters to the extraction process. So I'm completely new to coffee, don't know much of anything about it. And so for me, the important thing is the ability to experiment, to try things, see what affects what. And the AeroPress for me has been a much more efficient way to do that than any other kind of brewing. So I thought, why not see if I'm going to get into roasting, see if I can come up with a roaster that would be sort of analogous to that, in allowing me to make a small batch at a time, maybe take and buy a pound of green beans and then divide it up into 5 equal samples and roast each of those samples a little bit differently to see what effect the roasting differences have on my experience of the coffee when I drink it. So that was one of my criteria, and another one was the ability to have a wide range of control over the time and the temperature and the shape of the time temperature curve. A third criterion was the ability to reproduce or replicate any given curve so that I could do it again and have the curve overlay exactly what I'd done previously, or pretty much exactly. And then the last criterion I had was to have a system that would give me a uniform roast within a batch, so that I didn't have some beans that were roasted and other beans that were unroasted or roasted less, that all the beans would be pretty much the same within the batch. So those were my criteria. So I looked at on the internet a lot of possibilities, and one that seemed to be appropriate was modifying a popcorn popper. And that idea has been around for several years. So there was a lot of information that I was able to obtain, and I used a lot of it. In fact, most of what I've done here is based on the ideas of other people and their success. So I've added a few ideas of my own as well. But I think that where I'm at right now, for me, as a novice with respect to coffee, somebody that basically needs to be able to play, in effect, like children when they play, they learn what affects what. And so I'm experimenting, playing with all of the different parameters that are involved, and now I can do that with roasting too. So I guess, and I would also say that what I'm going to demonstrate in this video will not include the details. If you are interested in experimenting yourself with popcorn popper modifications, if you'd like to see the specifics of what I've done, it's posted on homeroasters.org. That's homeroastersplural.org, and and I'll give a link at the end of this for how you can find what I've posted. But if, let's say, you're not interested in popcorn poppers per se, if you're interested in roasting in general and you haven't seen homeroasters.org's site yet, I would highly recommend it. I was amazed the first time I went there at the number of different possibilities there are to roast coffee at home, people have thought of. A lot of things I never would have imagined. And it just goes to show you how creative some of these folks are, and it's really interesting to see. So if you haven't seen it, I highly recommend it. I think you'll probably wind up being a member like I am. Okay, so I guess that's about it for the introduction, and now I'll just explain what the equipment is and how it works. The popcorn popper part of the modification was pretty much like other ones that have been done over the past several years, in which the power to the blower motor and the power to the heater coils is separate, so that you can control each one independently. And that allows you to have control over the roast profile that you would not have if they were working together as they are when you buy the popper. So that was one of my criteria, so I did that. And those are controlled by the components in this box, which I'll get to in a second. Another thing I did was add a thermocouple, which you can see the thermocouple connection here. I don't know if you can see it. It goes through the back here into the roasting chamber. You'll be able to see that in a subsequent section of this video. And I put some extra holes around the base just to make sure that there was no restriction of airflow. I don't know if that's necessary, but I figured it couldn't hurt anything. And then the idea came to me also of changing the geometry of the bottom of the popper. This particular one, instead of circulating the air like many of them do, this one just shoots the air straight up. So what I did was, to get a funnel, I got this at Ace Hardware, very sort of thin aluminum funnel, and then cut it down in this kind of a shape. And that got pushed into the bottom here. You'll see that more clearly in another section of the video. And what it does is it increases the wall angle to 60 degrees from 45 degrees, and it also it also directs the air coming in through the center of the bean mass, which gives you, I think, better motion in the beans. And the third thing, it's aluminum. So aluminum is has very good thermal conductivity, so it will eliminate any potential hot spots that are in there relative to steel. So that's another thing that I added. So other than that, one other thing was I decided to remove the rectifier diodes from the motor and move those to inside this control box, and I beefed up the rectifier diodes as well when I did that. So anyway, in terms of control, the heat that goes to the heating coils is controlled by this knob here. And what this knob does when you turn it back and forth is change the percentage of time that the line voltage and power, or whatever it's plugged into the wall at, the percentage of time that will go through the heater coil. So if I turn it all the way counterclockwise, it's 0% of the time, and if I turn it all the way clockwise, it's 100% of the time. And similarly, I can pick any percent in the middle and thereby control the amount of power that's going through the heating coils, and thus the amount of heat that's developed and going into the popper. So that's basically that. In terms of the blower motor, because we disconnected the motor from the main source of power, we have to supply us another source of power, which is a 24-volt transformer, and that's inside this box. And the 24-volt AC secondary of that is rectified, and then that DC voltage is sent through this cable over to the popper. So it's now getting DC voltage, and there's no diodes in there anymore. So this knob controls the blower motor to a certain extent. This is just a dimmer switch. It's a single pole dimmer switch that is in the circuit for the hot wire that goes to the transformer. So if you turn this up and down, you control the voltage that goes to the transformer primary, and that in turn affects the voltage that comes out the secondary, which affects the voltage that goes to the blower motor. And you see here that this would be, if it's full power, it's turned all the way up, but you can only turn it back a certain distance. You would not want to have this knob be one of the knobs where you can push it to start it and stop it, because you want to make sure, at least I wanted to make sure, that the unit would be on, the blower would be on all the time when you turned it on, and so that it would be impossible to turn on the heating without the blower being on. So for example, if For example, if we turn this on, the blower comes on and the fan comes on, and then we can also, at that point, turn on the heater. If we don't have the blower on, we can't turn on the heater. But so this only turns back so far. If this were to go all the way back, and you shut this off, then it would be possible to turn this on and the fan wouldn't come on because there would be no power to it, but you'd be able to turn on the heater. Now the reason that that's important, I found out with the first popcorn popper I got, when I turned on the heat without the blower fan on, and instantly it stopped working. And I took it apart and found out that there's a thermal fuse, an aluminum fuse in there that melts at 250 degrees. So just in a matter of a few seconds, it had melted that fuse. So I decided, okay, well now I understand the principle of this, so I bypassed the fuse, and I also bypassed a bimetallic sort of temperature control that was in there. And I said, I understand this now, I don't have to worry about that. And put it back together, and it worked. And about 20 minutes later, I made the same mistake again. But this time, it overheated to the extent that it actually melted the impeller from the blower and ruined the blower motor. So while I was waiting for my next popper to come from Amazon, I had a chance to think about this, and I thought, you know, if I'm going to be operating this, I have to make it absolutely foolproof. So that's why I did it this way. There's a stop in here. You can't turn this off. I mean, I could turn it off, but it would have to be an intentional act to do so. So I turn this down. It's a minimum level. It's about a 10% difference here in voltage, which translates into about a 20% difference in power. And as far as for my use of this, I don't think I'd ever need to turn it any lower than that. So this is just limited here so that anytime you turn this on, the power's automatically on, and then you can turn on the heater. Okay, let's see what else. You see that there's a fan over here. This fan brings air in, ambient air, and then the air cools the device that controls the heater coil voltage. The air then flows across the unit through the diode rectifier, and it comes out here, and right inside of here is where the transformer is. So it helps to cool the transformer a little bit too, but the cooling that takes place there is negligible because of the mass of the transformer. A couple other things. This is a digital scale that very inexpensive, battery operated. And because I'm weighing every batch to 91 grams, which is 1/5 of a pound, this just pops out, and then you turn it on and you put everything on there, and you can weigh 91 grams. It's important to me to have exactly the same charge weight inside of here every time, because if I put more charge or less charge in here, it's going to affect everything else. So I want to keep that constant for what I'm doing. Let's see what else. In terms of the back here, if you want to see, this is the main power switch. This is just a series of connectors that I decided to put on here for development purposes, that I can plug my volt ohm meter in here to these two and get AC voltage coming off the secondary, and then I can get rectified DC voltage coming out of the rectifier here if I want to verify what that is. And then the other thing is, you see this thermocouple that's coming out of here. Well, one of the things I've learned from this is that the rating for the transformer in this case is higher than I originally thought. What I started out with is a 40 volt amp transformer, which roughly means 40 watts. And I used that for many months. Never really thought about it much, and then I got another transformer, which is right here, which was also 40 volt amps, and this one didn't perform, even though it's rated the same, anywhere nearly as well as the first one I had in terms of heating up. So any of these transformers heat up at a certain rate, and that rate depends on the load that you put on the transformer and its rating, among other things, and ambient conditions. So in two roasts, this one heated up to like 170 degrees Fahrenheit, which is close to what I would consider to be the maximum case temperature that you should tolerate. The other one was only like 150. But what I decided to do was just permanently mount a thermocouple to the case of the transformer, so that after every batch, after I let the unit sit for a while, so that the coils can let their heat go out to the case surface, I can measure the temperature. And if that temperature starts to, say, get above 150 degrees Fahrenheit, I just stop roasting, let it cool back down to room temperature, and then I can do roasts again. But I've done 3 or 4 roasts with the 40 volt amp transformer, never had any problems. And this one has a 50 volt amp transformer in it, so I'm not expecting to have any problems with this either. But I think this is a good thing to have on there, and to just routinely check the case temperature when you're done with a roast, and that way you can avoid overheating the transformer. So the other thing, I guess, to mention is this gauge. I can turn this on. You see here, there's 2 numbers. A number on the top and a number down below. So I'll turn this off so I can explain what those are. The number on the top is this is actually a voltmeter. The number on the top is really sort of like an RMS voltage from the output of the percentage time this is on and off, and you could think of it like the DC volts that would be required to produce that amount of power. I don't even worry about that conceptually. I just use it as an index number for how much heating I have this set for. So, for example, I'll typically start a roast with this set at 55, and then I increase it 2 or 3 numbers every minute, and that generates the kind of a profile that I'm looking for. The bottom number, this comes with a toroid that measures amperage if you put it over one leg of an AC line. So I decided to put it over the AC line for that comes out of the secondary on the transformer, so I can see how many amps the transformer is producing, and then I can measure the volts, so I get an idea of what the volt amp load is on the transformer. And the way it works out is that when this is set at the low level, you're below the rating of the transformer, about 45 volt amps, and if you turn it, you're above about 10% over. So I think that I'm comfortable with that rating on the transformer for this. Okay, so that's about it. And the next thing we'll do is I'm going to put some beans in here and take some pictures so you can see some video pictures, so you can see what the bean motion looks like under different conditions. I'm not going to do that during the roast, primarily because I don't like to hold the camera over. There's a lot of very hot air that comes out of here, and I'm not comfortable holding the camera over that. So I thought I would just do it now with the green beans, and then at the end of the roast with the roasted beans. This is the inside of the roasting chamber with the funnel insert in place. This increases the wall angle to 60 degrees versus 45 degrees, which is comes with the original base of the unit. And you can also see the thermocouple protruding in at about the 10 o'clock position. So this particular installation, rather than riveting the funnel insert in place, I've basically glued it in place with RTV, high temperature RTV silicone, which is elastomeric, instead of rivets, because the rivets can impede the flow of the bean somewhat. The other thing is that it's important to have the diameter of the base exactly the same as the air inlet grid from the popper, which is about 28.3 millimeters in diameter. and to make sure that when you insert the funnel insert that it is fully down and in place and properly situated with respect to that grid. Okay, now I've placed 91 grams of beans in the roasting chamber, and I'm going to start out by running this at the lower blower speed and let you see the bean motion in the chamber, and then I'm going to turn it to the higher speed. And I also have attached a chimney to this so that the beans don't shoot out onto the floor. And then I'm going to do the same to lower and higher speed, try to do it at slow motion. Okay, so this is at the slower speed. You can see there's considerable motion of the 91 gram charge. Now I'm going to turn the speed up to the high speed. Okay, so now we see I'm actually getting beans shooting out onto the floor here. So I'm going to put those back in and try to do this in slow motion so you get a better idea of what's happening. For the first half of this, we'll see how the beans are moving at the lower blower speed, and then halfway through I'm going to turn up the blower speed and you can see the difference. But generally they come up from the center and then they fall out towards the outer edges and work their way back, and now we're in the higher speed mode. You can see it's a little bit more action happening, and they work their way back down where they're shot up from the center again for thorough mixing. Okay, now I've increased the charge weight to 113.4 grams, which is a quarter of a pound. And you can see that at the lower blower speed, there's still a fair amount of movement, but not as much. So I'm going to turn it up now to the higher blower speed. And you can see at the higher blower speed, there's probably a sufficient amount of movement in there to do a roast up to a quarter of a pound. As I said before, I prefer to do the smaller ones, sort of micro roasts. It affords me the opportunity to do more experiments. Okay, so I apologize for that lengthy introduction, but we're finally ready to do a roast, and we're going to do it indoors today because it's been kind of rainy and cold here in Chicagoland. So I have the thermocouple plugged in from the popcorn popper, and you can see it's reading about 22 degrees C as a starting temperature, and I have a timer up here that's set at 0. So you can probably also see this record sheet, and I'm going to be roasting some Tanzania Mara Taremi, I think you pronounce it, coffee from Sweet Maria's today, and I have 91 grams weighed out, pre-weighed. So we're going to be roasting that using a fairly, what I use as a standard roasting profile. And if you can see on the sheet here, the sheet contains the target values, and there's a place for you to record the actual values each minute and the voltage settings off of this gauge as the roast proceeds. So that way, if you wanted to duplicate this, you just would follow the same settings each minute and you'll end up with the same results. So I guess that's about it. I'm going to just do this like for the first minute or so, and then we'll have a break, and then we'll pick it up at about 6 minutes when right before first crack is going to start. So what we're going to do is I'll first put the beans in the hopper, and then I have two what I call passive chaff collectors that I've done, and the first one is this one, and if you're unfortunate enough, excuse me, as I was, to destroy one of the poppers, you wind up with this part as a consolation prize. This is actually the base that I cut out. This is where the air would come through ordinarily. And the reason I use that is it fits pretty perfectly within the top of the popper. So these are, I call them passive shaft collectors because they don't rely on any kind of cyclone separation, rapid air movement. They're just simply filters, basically, that allow the chaff to be collected and then drop back down into the collector. And you know, I've been asked, how do you know that's not plugging up the collector? And I did an experiment, which is posted on homeroasters.org, where I used an anemometer to measure differences in air velocity as a result of numbers of roasts. And I was able to do 3 roasts and didn't notice any significant or meaningful change in air velocity. So I think you can do at least 3 roasts before you clean this thing out. So anyway, we'll put this on here, on top of the beans, and then should be ready to turn on the blower. And you can hear the beans moving around in there. I think I'm going to start out sort of in the middle of the range on the lower speed. You can hear them moving. I don't want to turn it up too high because the beans actually come out and go into the chaff collector, some of them. So now I'm going to turn on the power, and I have to turn it up to about 20 before you can start to see a reading. And so I turn it back. You can see right about 20, you can start to see a reading. And this would be 22, it's 22 volts, but figure it's like 22% power and 2.6 amps on the motor. So I'm going to start this, I usually start these at say 55. And it's kind of touchy. And then as soon as that happens, I start the timer. Okay, so what I'm going to do is, so it's 57, so not a big difference. So what I'm going to do is each minute, I'm going to record the temperature, and then I'm also going to record the change that I make in this setting. And I'm just going to continue to do that to try to match the target values that I have. The first target value would be 90 degrees for the first minute. We'll see how close that comes. And then I'll turn this up a little bit, and there's another, next target value is 118, and so on, throughout the roast. So I'm going to do this for like the first minute. So we're coming up here on the first minute, and we're right around about 90 degrees, just as expected. So I'm going to bump this up a little bit, and now I'm going to turn off the camera and go through most of the roast, so you don't have to watch it. It's kind of boring. And then towards the end, we'll pick it up again. So now we're right at 6 minutes and 191. And I'm going to leave this set at 88 where it's at. So we should be seeing first crack pretty soon. Normally I shoot for like 7 minutes at first crack, but we'll see what happens. Alright, I heard one. I don't know if you heard it. There's another one. So it's 6 minutes and 40 seconds, 198. And we're starting to get first crack. So I would want to go 8 minutes and 40 seconds, maybe 2 minutes beyond that. So now, I don't know if you can see, we're up at 203 centigrade. You still hear the first crack happening. See a little bit of chaff coming out. The It's not perfect, but it's not a huge mess like it would be if we didn't have the chaff collector on there. And I don't know if you can see this, but we have this set at like 88, which would be, you can say 88%, and 2.2 volts on the blower motor at this point. The reason that dropped is because so much of the line voltage is being used for the cooling. Okay, I'm going to just turn this back a little bit because it's going a little higher than I normally like to see it. So there's 8. And first crack seems to have stopped. So I'm just going to shut this off at 8. This is a little shorter than what I would normally do, but it is what it is. So I'm just going to shut this off now. And now it's on cooling. So it was shut off at about 8 minutes and 15 seconds. So you'll be able to see what happens if you look at the cooling in 1 minute. Should be down under 100 degrees, and right around 150 there's no more chemical reactions happening as I understand it. So we turned it off at 8:15. And so at 9:15 I think we should be under 100 degrees C. And then at 10:15 we'll be at 50 degrees C, and then I can remove the chaff collector without any gloves or anything. It will be cool enough for me to just pick up and remove. You can hear the beans moving around in there. They're still moving pretty good. Okay, so it was 8:15, and now we're coming up on 10 minutes. By 10:15 we should be under 50 degrees C. Okay, and there we are at 10:15. We're at 53. So the heat's been shut off. I'm going to turn the heating control all the way back just so I don't forget to do that. And now I'm going to turn off the main fan blower and just remove this. And you can see a little bit of chaff came out of there. I'll show you a little bit later how easy that is to clean up without making a mess. If we look at the roast, if you can, hopefully you can see that, there's very little chaff left in there. I'm going to just move this over and pour it out into this for now. And then, like I said, I want to show you, if I put this back in there, now that it's cooled off, I can hold the camera over there and show you what the bean motion looks like. So that's good. It all came out of there, and that's what we have. So, and you can see it appears to be fairly uniform. I could spread it out on here, maybe a little bit more. I don't know if it would be a little clearer or not to the video, but it does appear to be a fairly uniform roast, and that's been my experience with this anyway. So that's that part of it, and so now we'll have a section on reintroducing this, and you can see the bean motion, and then maybe one on cleaning out the chaff collector. Oh, I almost forgot. We said, you know, it's important to check after you've done all this to check the case temperature. So we started out at around 22 degrees centigrade. So let's see what the case temperature is. So it went from 22 degrees to 42 degrees with that roast, and that's, you know, that's warm. You could put your hand on that don't know exactly what it is in Fahrenheit right off the bat, but I think it's under 100 degrees. Well, in that neighborhood, 100, maybe 110, something like that. You can put your hand on it, you're not going to get burned. And if you did a second roast, it might go from 43 to 80 or 90. You could easily do with this, you could easily do, I'm saying 3-4 roasts and be well within the maximum case temperature. So, but you have to check it after every batch just to make sure.
I failed to record the rest of the data for the batch we just roasted, so I thought I'd just show you an example from a previous batch that I've done to show you what the time temperature curve looks like. This is another slow motion video of the bean action at the end of the roast at low blower speed and high blower speed, and I thought it was also useful in giving you an indication of the uniformity, within batch uniformity, among all the beans in the batch.
So cleaning out the chaff collector is really pretty easy. It's sitting in a sieve screen, and all I do is just run water into the top, and the drain isn't open, so I've got to close that. I'll open that up. Murphy's Law, I guess. There we go. So anyway, just run water in here, and basically what normally happens is that the chaff comes out into the screen. In this case, I guess a lot of it's going into the sink, but in the past, it's mostly come out into the screen, and then you basically take that, tap it in the wastebasket, and disassemble this, and which I'll just do for the heck of it, and put this over here. If I still have the screen there, I could get the rest of this into the screen, but basically, since it's wet, it's not going to float around the room or anything. Anyway, so that's basically it, and it's pretty easy cleanup.